Okay, so we're going to do one more example of finding flux through a surface. And so first I want you to take a minute, put it on pause and sketch, and then we'll come back in and check on the sketch, and then we will send you back off to try to set this up. Okay, so paraboloid, this is the paraboloid that's opening along the y-axis here, and I would like to know the flux through this paraboloid. We're stopping when y is at 1 here, and then the disk, x squared plus z squared less than or equal to 1 and y is equal to 1, that's just going to be this disk right here. And so I want the flux through this entire closed surface. This surface consists of this bowl and then also this lid here. And I'd like to know the flux. And when we talk about flux and I don't give you an orientation, then we're talking about net outward flux. So I want my n to be pointing outward at each point. All right, so notice this means I really am going to have to break up this integral into two different surface integrals, two different flux integrals, by the way. So let's call this first one S1 here, and then we'll call this one S2, and we'll have to set up a flux integral outward across F1 or S1, and then add that to the flux outward across S2 to get the total net outward flux. And again, in this, all I've drawn is the actual surface we're talking the flux about. We're talking about the flux. I haven't drawn the vector field. We have some vector fields here that's moving through my region. I'm not saying that's what it looks like. I'm just sketching a random one to help us remind ourselves we have things flowing around in this region. All right, so now put it on pause, and I would like you to at least try the setup for both of these, and we'll come through and walk through it together. All right, so first one, let's talk about S1. First integral is I need to write S1 as a level surface. And so the paraboloid is y is x squared plus z squared. One way I could write that is y minus x squared minus z squared. If you do it that way, then your g is going to be given by y minus x squared minus z squared. And then your gradient, in this case, will be negative 2x, 1, negative 2z. And you'll notice that in order to make it point outward, I'm going to need to take the opposite of the gradient from my particular point. And you can see that by just looking at what happens at 0, 0, 0. When x, y, and z are 0, my gradient is the vector 0, 1, 0, which is pointing like this, but I actually want it to point outward. So this would be the negative gradient, what I chose. You may have picked it, you may have written it as x squared plus z squared minus y equals 0, in which case, if this was your g, then the gradient you chose would be pointing the right way. So that's why everyone has to check, because there's plenty of different ways to write these as level surfaces. Okay, now we need to pick a coordinate plane where we can project. And again, I don't want this surface to fold on itself, this bowl, so it's going to be easiest for me to project this onto the xz plane in this case. And so I'm going to let p hat just be j hat. And then we're going to do some simplifying. So now I find f dot n ds, which is going to simplify to be negative y minus 2z squared dA. And I've decided to project onto the xz plane, so I need to put everything in terms of x and z, using the fact that S1 is this, my surface itself is y is equal to x squared plus z squared. So everywhere I see a y, I'm replacing it with x squared plus z squared. That's what I've highlighted in yellow there. And that is going to give me this integral negative x squared plus 3z squared dA over my region R, where my R is the shadow in the xz plane, and we can see that's now a circle. And so if you were thinking, oh wait, before you set up those limits, it looks like you should switch to a version of polar, you're correct. But now notice, when I switch to this version of polar, I'm going to still let x be 1 cosine theta. But now I don't have a y, I have a z. So I'm going to think of z as 1 sine theta. And then I can switch everything to polar. There's the Jacobian, and then it's just plugging and chugging through this math, and it's going to give us negative pi. Okay, so now that was only part of the surface. Now we need to go do the lid. So let's look at the lid now. Okay, so now I need to write S2, which is the lid, as a level surface. And this is usually a really hard part for people to think of. What is this actual surface that's the lid? If you just were describing the surface, it's part of an entire plane, y equals 1. Yes, this x squared plus z squared is helping us determine what part of the plane we're looking at, but that's really just going to help us with the shadow. It's not helping us with the surface itself. The surface itself is literally just coming from part of this plane y equals 1. So my, this surface here, so my g in this case is, I can just let g be y. And then you notice that your n is just 0, 1, 0, which you could have seen probably just visually. You notice that this normal vector needs to just point out here in the direction of j hat. Okay, so now we are going to project. I'm going to still project onto the XZ plane. That's the easiest one to project that pink lid onto. And so now my integrand is just going to become y dA. But I need to rewrite it because I need it in terms of x and z. So I come back up to my surface and notice that y is just 1. So I'm going to replace y with just 1 dA. And now this is really just asking me for the area of the shadow. And so I can set it up if I like, or I can just use geometry and realize, oh, it's the area of the circle of radius 1, so it's just going to be pi. And then I go back and add this now to the flux across the bowl that I got from part A, or from the beginning part, and I notice that the total net outward flux through this bowl with the lid is 0, which I can interpret as meaning the water that's flowing through this, I have the same amount coming in as going out, so my net outward flux ends up being 0.